Hello, community! So great that you are back. Yes, it's summertime in the northern hemisphere of our planet, and therefore we have time to look at new AI architectures. The next model that will come out here later this year. Let's have a look at the breakthroughs. Now, you remember in my last video I talked about your neural graph architecture, complete new distributed neural architecture instead of our transformer networks, and you noticed there was a little paper in the background that I told you a little bit later on. Huh? Now is the time. Now we do have the time to look at this particular paper. And of course, we start here. We have to understand what are the limitations we want to tackle, how we want to optimize, what elements we want to optimize. Therefore, let's have a look at the cracks in the LLM facade. Shallowness. Our transformer has a fixed and relatively shallow number of processing layers. Not really great for complex multi-step algorithmic reasoning, no? Yes, we can make it wider, but this doesn't really help, no? And we can't make it deeper, but this also hits a wall. Also, our chain of thought kind of works now by externalizing here the reasoning process here, but it's rather brittle reasoning and it struggles here with problems that require more complex reasoning. And in plus, for the training, we have an extreme high data inefficiency, which would require massive data sets. So what about a new idea by this company, Sapient Intelligence in Singapore? I am not sponsored or I don't know this, I just encountered it the first time. But by the way, they are hiring, so if you're looking for a job in Singapore and the San Francisco Bay Area, there are job openings over there. And I have to tell you, their paper is really interesting. Also a little bit confusing. Let's dive in. Now they start telling us, hey, look at our models. Here in blue, we outperform everything. We have here AGI 1 benchmark data, AGI 2 benchmark data, but just look here when all the other models from an O3, a Claude, a DeepSeek R1 have exactly 0 performance. Look at our benchmark data for a Sudoku 9x9 or 30x30. Look at this just with 1000 training example. We have some excellent performance, and you would ask, how is this possible? Now, the basic idea is relatively simple. Yeah? You have 4 learnable components. You have an input network and an output network. Great. And we will talk about the functionality of both. And in the middle, so the main workhorse, you have a recurrent module for a low-level computation and a recurrent module for a high level. And we just talked about modules here in a sequence for a path in my last video, so you are familiar if you have seen my last video about the module thematic. Recurrent simply means RNN, recurrent neural network, LSTM, whatsoever. Now you know, as a subscriber of this channel, that standard RNNs have a fundamental limitation. They converge far too early. This is not really what we're looking for. And now this new methodology has a simple fix if you want. They say we have 2 interwoven loops. We have a cycle with here a L module. This is an RNN, as they tell us here, as this is a low module, and then we have an H and high module, and somehow those 2 modules here interact here in an interwoven 2 loop state, and this is the solution that we do not have this immediate convergence, but we have a hierarchical convergence. This is much more powerful. Sounds easy. Here you have a screenshot. This is the explanation. You have here in this new methodology an input vector and you have an output prediction vector. This is it. And you just have to learn the in-between. And here we have, if you want, here our low component, and here we have our high performance component. And this is it. This is the update mechanism. And here, why this is exactly here our output function. So you say, could not be easier, no? And you immediately see here, okay, 0 modulo t. So if I has certain multiples of t, then we have an update process. Otherwise, we go here with the old value here of the state function. So this looks simple almost, yeah? So what it does here is a little bit more advanced. And if you read the paper, they jump into a high detailed discussion. So maybe you are not really that you say, okay, I understand here the details. So I want to produce videos that you can understand the idea right from the start. So I show you now a different perspective of this paper that is more easier to understand. It starts here from the beginning and gives you some introduction. and then we can have a look at the implementation details. So what it does, this new methodology from a hierarchical reasoning, a sequence of distinct, stable, but nested computation in multiple loops. So our high module directs here the overall problem-solving strategy, and you think, hey, this is like an agent, no? Our coordination or orchestration agent. And then we have a low module, like a worker module in the good old times, and this execute now an intense search or a refinement required here at the step. But the real intelligent way is now to combine this in an interwoven loop process that the hierarchical convergence benefits here are somehow integrated here in the loop structure. It sounds complex, but it's not really. However, if we look now at the three models, no? In black we have our transformer model. Here we have the depth or the transformer layer that are computed against the accuracy that we achieve. And you see with a classical transformer, 256 layers, beautiful. With a recurrent transformer, it's a little bit bigger after a threshold, and you see we're here. But what we are talking now, this new model, this is here the blue one. Look at this. This looks now really interesting with the performance reaching 100%. So let's have a look at this two loop cycle or this two element cycle, this two module cycle. The trick is relatively simple, no? You see here, if you look at the forward residual and at the number of steps, so the H module, this is here in orange, the H module steadily converges. Beautiful. While the L module here in blue, you see the spikes, the residual spikes. Before it converges, then it's get another input from the strategy, and then it converges, gets another input, another. So this is here beautiful. You have here the strategic dimension if you want, and you have here the work dimension where it's tried out and optimized and tried out and optimized. And then the strategic worker looks at this, implements here a new strategy, and the worker is implementing this and is getting better and better and better over time. So it's an easy idea, no? Well, the problem is now, of course, here in the implementation, because our recurrent models here, no, they typically use here BPTT, the backpropagation through time, to compute the gradients. And this is everything else than an easy forward task. Now, there's now a trick, I would call it, that in our new HRM model, we have a one-step gradient approximation. Mathematically, they derived it from a deep equilibrium model, which employs the implicit function theorem to bypass this. But if you're interested, you'll find all the mathematical formula in the paper. However, what is interesting is that this HRM is, if you want here, on a high abstraction level, absolutely a recurrent system. It maintains hidden states that are updated iteratively over time. So we really do have a recurring dynamic that allows the model to perform here a variable number of computational steps and achieve computational depth. And this is what we're looking for. Not just 12-layer deeps. No, whenever the strategy tells us, hey, I'm not satisfied, go deeper. The worker does it, comes back with the result. Strategy says, not really satisfied, go deeper. This is where we get additional depth here. So you see, it's a simple idea. However, if you implement it now on the architecture level here in the update engine itself, if you read the paper, and this confused me at the very beginning, so the first 10 pages of the paper, thinking about RNN, in reality, it's not an RNN, it's a transformer block. So this is something, be careful, I just want to tell you this. So when you look inside the recurrent loop, and the function that actually computes the next state for the previous state, you find here a transformer block. So careful, we are not operating on RNNs, we are operating with the idea, the abstraction of RNNs, but we implement it in a transformer block. This is our module, and this is our path forward in the graph network. Now, if you're not really familiar, 3 years ago I did here already a video that I showed you if we have here the transformer block in itself, we can halve it. Yeah? The first half is more or less what we call a BERT system. Transfer learning, continuous learning from existing data, great. And then the other half of the transformer block is what we call the GPT from OpenAI. No? this is where you get here really the next token prediction. So careful. Now we are talking about the encoder part. It is not like a T5, the complete transformer block, but it's just the encoder block, or if you know it, BERT, or for sentences, SBERT. If you're not familiar with this, never mind, you came to the right source. Here you have SBERT. I have more than 40 videos. I explain everything about the BERT architecture from the last 2.5 years. And if you want a high-level overview, here's it. As I told you, we have 4 components: the input processing, F input, the output processing, function output, and then the low-level module, L, and the high-level module, underscore H. Now you see the architecture that is really implemented is now standard embedding, an encoder-only transformer block, also an encoder-only transformer block, so this means BERT. And then the output is a standard linear layer and a softmax. I will show you an example in 5 minutes. So, a standard transformer, now let's make it clear the differences to the standard transformer, is feed-forward and fixed depth. So information flows once through the static number of layers. Now this new model, hierarchical reasoning, is recurrent and has a variable depth. So the information cycles to the same transformer blocks multiple times, allowing here for an arbitrarily deep computation that is only controlled by the ACT mechanism. I will explain this in 2 minutes. Now if you compare this new HRM with the standard RNN like an STM, a standard RNN is also recurrent, but its state transition function is rather simple. So this limits its ability to model the high complex relationship within a single step. But now in this new methodology, which is also recurrent, but now the state transition function is a full self-attention block. Yeah, making each step of the recurrence now much more powerful and expressive. So you see, it takes the best of both worlds. Now, of course, as a subscriber of my channel, you know we already had this, no? The universal transformer, which was a recurrent transformer architecture. So the idea of applying a transformer block recurrently is not entirely new, no? The universal transformer did this. However, compared now HRM to this universal transformer, I want that you understand that there are 2 main differences. In the temporal separation, no? It doesn't just have one recurrent loop, it has 2 coupled loops operating at different speed. I'll show you this in 1 minute. So we have this high and low structure is what prevents here the model from fizzling out and enable a stable, long horizon reasoning performance. Plus, I already told you about the one-step gradient approximation. So coming back now to the technical terms, the jargon, yes, this new system is recurrent, as in a state definition that every system is recurrent if its computational graph, see last video, contains here a cycle. And this is the case. But it is not an RNN, but it is, from the architecture, a transformer block that has a graph that contains a cycle. So you see, easy. Don't get up here in the technical terms because it is not implementing an RNN architecture, but a transformer architecture. I need another moment of your attention, another trick that you have to understand: adaptive computation time, ACT. Now the challenge is training now here a recurrent model for some long reasoning traces. Not this simple one, but really the long monster reasoning traces. No? And if you only provide now the loss at the very end after 100 of steps, you know, the gradients have a very long and difficult path to travel backward in the backpropagation, making the learning absolutely inefficient and unstable, and we know it's not working. So is there another trick or methodology that you can apply? And the solution is here, yes, of course, we call it deep supervision. So instead of one single massive forward pass, this new method breaks here the thinking process into a series of smaller forward passes, which the paper here the authors call segments. Have we heard this before? Well, yes, of course. And it is called deep Because as a deep supervision, and the supervision is nothing else than a loss calculation methodology, is applied at multiple depths of the computational process and not just at the very end. So you understand? Simple, no? This results more or less in three benefits. We have a frequent feedback. So if you think about it, it's a teacher in a classroom, no? Teacher checking in every 5 minutes instead of only checking at the end of a 2-hour exam. It makes learning much more stable and much more efficient for each student. Regularization. This is kind of a natural regularizer, improving here the generalization, and it is the foundation for ACT. So, let's have a look at ACT, adaptive computation time. Now that the reasoning process is broken into discrete segments, as I just showed you, now the model needs only to know, hey, when should I stop? Should I run for 1 segment, 8 segments? When is the right time to say, this is it, this is the right result? And this is now where ACT comes in. Yeah? It is like a second head here on our transformer, on the model, that acts now, and now hold on, because it acts like a tiny reinforcement learning agent. And you say, wait, is it now possible that we really come now and we can use our knowledge of reinforcement learning? Because now we have here a second head on the ACT mechanism implementation on the deep structure? Yes, exactly. Now things get great. Now, if you want to know the details, this is here for you. We have here a Q head. So at the end of the segment here, this head looks here at the current hidden state and predicts 2 values. Q hold and Q continue, and yes, you get it what it is. And then we do have a decision rule. So either the model decide, give a new instruction on your hard-coded rules when to hold or not. Learning these Q values from RL, you know how it works, great. So your reward for for halting, not for halting. Huh? Now, if the model halts and the answer is correct, the reward is +1. If not, the reward in the simplest case is 0. For continuing, you get the idea. So this is our standard Q learning setup that we know here from reinforcement learning. And we just apply this now here because in our new methodology, we also broke up the thinking process into many segments. And now we simply need here the reward function for each and every segment. So the complete flow of the process, now of this whole is now as follows. ACT decides if another segment is needed. If yes, the deep supervision loop runs here the core recurrent mechanism for n times t steps. It gets an answer, calculates a loss, and loops back to the ACD for the next decision. So we have kind of an elegant interplay, and this is what makes here this new model quite powerful and efficient if you compare it to the traditional example. But let's have an example. Imagine you have a Sudoku grid 9 times 9. This is here the initial, this is it. No? Now, to feed this into a neural network, we have to build a vector. So how you build a vector from a Sudoku grid? Well, it's easy, you know it, it's called flattening. So we turn this 9 times 9 grid into a one-dimensional flat vector of the length of 81. So what you have, grid 0, 0, grid 0, 1, grid 0, 8, and grid 8, 8. So you understand the methodology. And then we are talking about transformer. We have to have the tokenization process. No? Each cell in this vector contains now a specific number from 0 to 9. Or 0 might also have here this absolute blank cell. And then we treat these numbers as tokens. And the model needs to predict the token for each of those 81 positions. Look how easy it is to transform a Sudoku into a high-dimensional vector. But now the main question is, how can we train this new architecture? No? Because before we can switch it on, we have to train it. We have to pre-train this thing that it has intelligence, artificial intelligence, hopefully. So the training process, let's have a look at this. Now, when you start with an input and with the final result, because it has to learn the steps. No? The input is easy, a sequence of 81 integer token for our Sudoku puzzle. No? So those are the numbers that are already filled in. And then we have to provide the final solution, the target. Yeah, X and Y, whatever you want to call it. And the target is now a sequence of 81 integer tokens representing the correct final solution. Easy, it's a vector with 81 components. Great. So let's come now to this thinking process that is happening in the training. Yeah? So in this new HRM methodology, it runs its recurrent high and low loops for a full segment, so n times t steps. And this produces here a final high-level state vector. I'll show it this in more details in about 5 minutes time. So let's call it z underscore h final. So this vector is now the model's conclusion after one segment of sorts. But this is just the beginning, né? Because now in the decoding step, final state vector is passed through a simple single output layer. And this layer is just the linear transformation followed by a softmax function. And this has only one job to do. Translate the internal sort vector, and this is a high-dimensional sort vector, let's say 512 or 1028 dimensions, into an answer in the required format. And the format that we need for Sudoku is here a lower dimensional vector representation of the Sudoku. So let's say 81 dimensional only. Ne? So this is simply here exactly the decoding step. Now, if we have this prediction here from the first step, you know what we do? We have now a loss calculation, a cross-entropy loss. No? The model now compares its prediction here after the first step with the ground truth, with the golden final solution, and we just predicted the loss. And for Sudoku, this loss measures here how different the model's proposed solved grid is from the actual solved grid. And then we have the classical methodology, backpropagation, everything that you know. The model learns to adjust itself. The model learns over 1,000, and this is here what they say, hey, after 1,000 training examples, we already had a good model, the authors tell us, no? And also, when I see this kind of input puzzle, my internal here vectors here for low and high, these are now a vector representation, because remember, we are not working in GPT to predict the next token. No. We are here in BERT. We are here in the encode of a transformer block. This means we are operating in high-dimensional vector spaces only. We only have vector operation as our mathematical toolset. So, we have built those vectors. They need to follow here a particular trajectory. You understand immediately if you have seen my last video about trajectory optimization. And that trajectory must lead now to a final vector that is a very specific point in this high-dimensional vector space, that is a latent space. And what is this specific point? Because the model says I have learned that only some specific vector, when passed through my output layer, produces here the correct final solved puzzle that matches the training label. This is here the training step that the model learns. So you see the reasoning in the training is completely different from any GPT or I don't know, go with any anthropic model or whatsoever. We are back here to BERT. Now this output layer is something really nice. Now I've given you already an example, but let's have another look. So after HRM has finished its internal thinking process, it has now a final high-level state vector. Let's say 1028 dimensional, or 512 floating point numbers in this vector. No? Now this is, if you know, a compressed representation of the solution of a puzzle, of Sudoku, of whatever. But it is a representation in a high-dimensional solution space, a vector space. And it is not in the 81 token format we need as a representation for the Sudoku solution. And this is now where our output layer transformation comes in. The output layer has only one job to do: perform this final translation from 512 to 81 dimension. It learns it. This is it. So its only job is to translate the internal sort vector, if you want, the thinking vector, into an answer in the required format for our task, for the puzzle, Sudoku, whatever we have. The way that this is done is simple. No? We have a linear transformation and a softmax function. Great. Now I think it's easy from this kind of perspective, looking at this new model. You don't start with heavy, detailed implementation, but you try to understand what is the general idea. The general idea is the new model is also an optimization. And you have here in the training process, let's stay with Sudoku, or 9 times 9 or 30 times 30, whatever you have, yeah? Where all the other GPT models with next token prediction fail because we don't work with GPT or the decoder part of a transformer block. We work now with the encoder part only in the vector space. So therefore our training is different. Our training is now, in the pre-training if you want, we have a start condition from Sudoku and we have the final solution of Sudoku. And now we let the new AI model just run and run and run and find its internal representation that is the solution. The way it does it is not really known. Somehow in this neural network it happens. It is not as elegant as in my last video. So the HRM model doesn't know about tokens or the logic rules that it is applying. It is just trying to find a solution from its pre-training dataset. It only knows about minimizing here the loss function between its finally decoded output and the ground truth label. This is all that there is. So it learns to perform here the necessary latent computation. This is this vector dance, if you want, that leads to a final state vector which really represents the solution. And I've showed you how to transform a Sudoku into a state vector, a high-dimensional state vector. The recurrent operation. If you are still into details, have a look. If not, hey, great that you watched the video. Have a look at the paper. It's really interesting. If you have another 5 minutes left, let's have a look here at the recurrent operation here. It is, if you want here, this nested thinking loop that avoids here too early convergation, and it's a two-state vector and an update rule, if you want, in the basic. So we have this, if you want, low module, let's call it the worker, and this high model, let's call it here the strategist. And it's easy, no? The low module updates every time step, no? It performs fast, detailed computation based here on the strategic plan by the high module. And every, let's say 10 step, 15 step, 20 steps, whatever you decide, the high model, the strategist, comes in, looks at the work done by the low module, looks at it, says, some parts are great, but look at this particular part, we need another strategy going forward. And now the high model adapts the strategy, so the guiding for the low model, what to do next in the next 10 steps. And after those 10 steps, the high model comes back, have a look at the result, optimizes strategically. You can think about it like agents. But remember, these are not agents. This is a new LLM. This is the core, the brain of an agent. And you just let this run in cycles. If you want to see here the mathematical notation, if you prefer to see this here on a mathematical level, well, low-level module updates every steps, high-level module updates after every cycle, and the final output generation, we just explained this. This is simply here the mathematical notation where I showed you here. You have here our low performance transformer blocks and our high-level transformer blocks. I've told you if every 10 steps here, we do have here, if you want here, an update process. Otherwise, the high-level module does not come in for 9 steps. And the final output generation, we had to talk about this. Great. So if you take a step back and say, okay, what we learned today? What is now the core of this new model? And it sounds familiar. We know a lot of it. It is just a new configuration. No? Let's start at the data input, the data aggregation at the very beginning. No? What is it? It is something that we know. No? We have here x bar, our vector, representing here the original problem. Let's say the Sudoku grid. I showed you how to do this. Vector representation. Then the high-level state vector. This is the current strategy from the high-level module. And the low-level state vector from the previous steps. And then we generate from all of this a single new vector. And this now is the input to our first transformer block. So what the model does in the input aggregation, it just combines here the various sources of information in the input presentation and the strategy, and it just says, okay, let's go. Let's learn here an internal representation. Then the classical way, self-attention, the projection matrix, then the self-attention, the score calculation, how much attention each element should pay to every other element, then the value aggregation, create here a weighted sum of the value vectors, effectively here the routing information. And then we have our feed-forward network. Attention output goes through all the first linear transformation, a GELO or whatever you like, activation function, and non-linear activation function. And then we have a second lineation transformation. And then we have our residual connection. But remember, we have two, no? We have the first residual connection after the multi-head attention with a layer normalization, and this then goes into our second final residual connection after the feed-forward network vector, and this is now the final output vector of the entire transformer block. So it is a notation that we know, it is that we can handle this, but it has some real beautiful performance. So therefore, if you want to think about a new architecture for the next generation of AI models, I think this is kind of a brilliant solution. Eh? Overcome here the problems that we have in RNN, take the idea, implement it into a multi-loop transformer, interwoven system, and get the reasoning performance that you are looking for. If you want to see more videos like this, hey, why not subscribe? And I see you in my next one.